Every single time you turn on the tap, you're seeing the very end of an absolutely incredible journey. Water from a river or a lake or a reservoir, it has to run this complex gauntlet of engineering before it's clean and safe enough for us to drink. So today, we're going to follow that journey, step by step. Just think about it for a second. That glass of water right in front of you. It looks so simple, right? So pure. But getting it that way is anything but. What does it actually take to turn cloudy, raw water, full of who knows what, into something so clear and safe? Well, the answer is this amazing, multi-stage scientific process that's, frankly, one of the cornerstones of modern public health. All right, so the main challenge, kind of the villain of our story, comes in a really tiny package. Let's talk about colloids. These are microscopic bits of clay, silt, organic matter, all the stuff that makes water cloudy or turbid. The problem is, they're not only tiny, but they all have a negative electrical charge. It's like they're all tiny magnets pushing each other away, so they just refuse to clump together. If you just left them alone, they'd stay floating in the water forever. They're too small to filter, and they won't settle out. So we've got to get clever. And that brings us to the first stage of the gauntlet. We have to round up these microscopic fugitives. Since they won't group together on their own, well, we're going to have to force them. And this is where a little bit of chemistry comes to the rescue with a brilliant 1-2 punch.
First up is coagulation. We add a chemical that has a positive charge, we call it a coagulant, and we mix it in super fast. Instantly, this neutralizes that negative charge on the colloids, so they stop repelling each other. Then, right away, comes step 2, flocculation. Here, the mixing slows way, way down. You can think of it like a slow dance. This gentle stirring just encourages all those now neutral particles to bump into each other and stick together, forming these bigger, heavier, visible clumps that we call floc.
Now, engineers have a whole toolkit for this. They often use things like metallic salts, like alum, to neutralize the particles. Sometimes they'll even add these long chain polymers that kind of act like giant nets to sweep up even more debris. But here's the thing. This isn't guesswork. Every single water source is different. So for each one, engineers run what's called a jar test in the lab. It's basically a series of mini experiments to find the perfect chemical recipe, the exact type and dose to get the job done just right. All right, so we've taken millions of these tiny, stubborn particles, and we've herded them into big, heavy clumps of floc. So now what? Well, now we can let a fundamental force of nature do the heavy lifting for us. Good old gravity. The concept here is just beautifully simple. The water, now full of all this heavy floc, flows into a massive, calm basin. We call it a clarifier, or a sedimentation tank. Because the water is moving super slowly, the floc just doesn't have the energy to stay afloat. And so, gradually, it all settles to the bottom, forming this layer of sludge. And the water at the top, it becomes much, much clearer. But even this simple-sounding process has layers of complexity. Our floc undergoes what engineers call flocculant settling. What's cool about this is that as the clumps sink, they actually keep bumping into each other and growing even bigger, which makes them fall even faster. Really understanding these different types of settling is absolutely crucial for designing the most efficient tanks. So how does this theory get turned into a real-world structure? Well, engineers use a really key design parameter called the overflow rate. You can basically think of it as a speed limit for the water moving through the tank. For a typical plant, that might be around 20 meters per day. If the water flows any faster than that, the smaller floc just won't have enough time to settle out. This single number directly dictates how massive these sedimentation tanks need to be to handle a whole city's water demand. You get it wrong, and either your water isn't clean enough or you've spent millions on a tank that's way bigger than it needs to be. Okay, sedimentation took care of all the big stuff. The water is looking pretty clear now, but there are still some tiny particles that manage to escape gravity's pull. So for our next challenge, we need a much, much finer net to catch these last little stragglers. The early filters were pretty straightforward, just deep beds of sand. And they worked, but the fine sand right at the top would clog up really fast. The modern solution is so much smarter. It's the mixed media filter. This thing uses layers of different materials. It starts with coarse, lightweight anthracite coal on top, then sand, and then finally a layer of fine, heavy garnet at the bottom. This brilliant design lets particles get trapped through the entire depth of the filter, not just on the surface. And that means it can run longer and filter faster between cleanings. But of course, any filter is eventually going to get clogged. That's its job. So how do you clean one that's the size of a building? You backwash it. Operators literally reverse the flow, pumping clean water violently upwards through the filter bed.
This fluidizes the whole thing, shaking all that trapped gunk loose and washing it out to a drain. And just like that, the filter is reset and ready for the next cycle.
At this point, our water is crystal clear. You could hold up a glass of it and it would look absolutely perfect. But, and this is a big but, it is not safe yet. The most dangerous enemies are the ones you can't see. We're talking about the invisible assassins, pathogenic bacteria and viruses. I cannot overstate this enough. This is, without a doubt, the single most important step for protecting public health. All the hard work we've done so far has just been to remove particles. This final stage is about killing the microbes that cause devastating diseases like cholera and typhoid. This is the last and most important line of defense. So, for this final battle, engineers have a few different weapons in their arsenal. Chlorine is the classic choice. It's a powerful chemical that destroys microbes, but it also leaves a little bit of a protective residual in the water to keep it safe as it travels through miles of pipes to get to your house. Then there's ozone, which is an even stronger killer, but it doesn't leave that residual. And then you have a totally different approach, UV radiation. This uses powerful light to basically scramble the microbe's DNA so they can't reproduce. It's a physical process, no chemicals added. But again, no lasting protection in the pipes. And there you have it. The 4-step gauntlet is complete. Through coagulation and flocculation, then sedimentation, then filtration, and finally disinfection. That murky river water has been totally transformed. It's been clarified, polished, and purified into safe, reliable drinking water. So the next time you go to fill up a glass of water, just take a second to think about the incredible journey it took to get to you. This invisible infrastructure, working silently 24/7 right beneath our cities, it has arguably saved more lives than any single medical breakthrough. You have to ask yourself, isn't it quite possibly one of the greatest public health achievements in all of human history?